Welcome to a new lesson. In this lesson we'll be estimating roots. Let's first compare the meaning of estimation versus calculation. Estimation is approximation of what the actual value is. Well, for example, if you calculate the square root of 20 on your calculator, and I'm just going to have a little tail right there, you get the value of 4.472, and it goes on and goes on. This is called calculating, and this is an exact value. Well, if we have all the digits of this irrational value. What an estimation is that if I estimate root 20, well, it's approximately 4. That's what an estimation is. Now let's take a look at on the left picture, and we'll talk about the syntax and the naming of roots. There are three names that you need to be comfortable with. The index tells you what type of power it is of a root. The radicand, what's inside the radical sign, and of course what the radical is, which is the whole thing. So now let's talk about square roots and cube roots. Where a number x can be written as the product, that means multiplication, of two equal factors, then the square root of x is represented by the root of x, and is one of these factors. For example, root of 64 is 8 because 8 squared is 64. In other words, 64 is the same thing as 8 times 8. The cube root, however, of a number x represents by the cube root of x, is one of these equal factors of numbers. For example, cube root of 64 is 4 because 4 cubed is 64. In other words, 4 times 4 times 4, because it is cubed, is 64. So now what we're going to calculate the root of 144. The root of 144 is 12, because 12 squared is 144. Now the cube root of 27 is 3, because 3 cubed is 27. A power of positive integers, exponent, represents repeating multiplication. So 2 to the power 5 is the same thing as having 5 2's multiplied. The power has a base and an exponent. An example above, the 2 is the base, and the 5 is the exponent. The exponent represents the number of equal factors in a power. So we're going to write this expression as the power of 3 times 3 times 3 times 3 times 3 times 3. Well, there are 1, 2, 3, 4, 5, 6 3's. Therefore, it is 3 to the power of 6. So now we're going to write this power as representing multiplication. That means 7 to the power of 6 has 7 times, and there's 6 of those. And of course, don't forget the last 7. Now we're going to fill in this chart. We're going to focus on two things. We're going to see if it's exact root, approximate, or exact values for our radicals. And if we can estimate our roots, radicals, then we will also do that. So let's take off root 16. We just can do this in your calculator. You get exactly 4. Exactly 4 because we have no repeating or non-continuing numbers behind 4. What about radical 27? The value is 5.1962, and the numbers keep going, and that's why we call this an approximation. How about root 16 over 18? Now the value is 4/9, and that is an exact value. Even though in your calculator a calculator will look like this. Whenever we have a repeating values, we'll always refer to it as exact value. Also on the side, I want to show you how to do this problem without the use of your calculator. So let's say I have a root of 16 over 18. It's the same thing as having a root of 16 over root 18, which is the same thing as having 4. Oh, the book made a little bit of error. It's actually supposed to be not 18, but 81. So if you take a square root of 16, you get 4. If you take a square root separately of 81, you get 9. So we can approximate this value, or actually find this value, without the use of calculator. Let's take a look at the next row. We have root 64. Well, actually, not root 64, but 0.64. But honestly, root 64 has a lot of importance in this case. The reason why is because we know that root 64, or radical 64, is 8. And since we have 0.64, your answer will be 0.8. So your answer is exact because there are no other digits following 8 that are non-repeating. Let's take a look at the next example. Root, or cube root 16. In this case, use your calculator to solve for this answer. So press the math button. Then press the down button until you see 3 cube and bracket. And we will get the value of 2.5, and I'm going to stop at 2 decimal points. And it keeps going and going. It's non-repeating, and therefore our value is approximate. Now we'll take a look at cube root 27. And the answer is 3, because 3 cubed is 27. And this value is exact. So we're going to take a look at the last cube root, 16 and 81, not 18. And we're going to use the calculator to find our answer for this. Again, press math button, and then scroll down by pressing the down button until you find cube, bracket, and put 16 divided by 81. And our answer is 0.582, and it goes on and on and on, and it is an approximation because we're rounding off on the 3rd decimal point. In the next example, we're going to be trying to estimate without the use of calculator, that's what estimation means, to 1 decimal point, the root 40 and root 54. In order to do so, we have to find perfect squares that 40 and 54 lie between. So let's make a list on the right-hand side. So 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, then we have 25 because that's 5 times 5, and 6 times 6 is 36, and what's the next one? 7 times 7 is 49, 8 times 8 is 64. So take a look. 40 lies somewhere between 25, not 25, but 36 and 49. 36 and 49, that's where 40 lies. So it is between 6 squared and 7 squared. But how close does it lay between 36 and 49? It is 6 away from 36 and 9 away from 49. So it is leaning more close to the 6 than it is to the 7. So we know that it's the root of 40 is going to be 6, but it's not going to be half, because then it would be halfway between 36 and 49. But it's not halfway. It's more leaning towards the 6 than it does to the 7. So my approximation that it's going to be roughly 6.3. Actually, let's revise this. It's not 6 away, but it's actually 4 away, and from 36, and 9 away from 49. Now, how do I get that 0.3? This is a neat way to do this problem. How do I get the 0.3? Well, we know that it's 4 plus 9 is 13, and it is closer to the 36 by 4. So I'll take 4 divided by 13, and that will give me 0.3. Let's use a similar method to find the root of 54. Again, we have to make sure that we have the list of the perfect squares. And 54 lies somewhere between the 49 and the 64. It lies 5 away from 49 and 10 away from 64. So we know that our answer is, so that means it lies between 7 squared and 8 squared. So our answer will be always smaller, so it's going to be 7. And then do the same procedure. Take 5, divide by 5 plus 10, which is 15. And this will give us 0.3. And if you look on your calculator, root of 54 is roughly 7.348, which is a pretty good estimate. Let's take a look at different estimates. Now we're going to use estimation to find the cube roots. So now we have to make a list of cube roots. So 1 cubed, 2 cubed, 3 cubed, 4 cubed, and 5 cubed. You need to know those by heart. So 1, 8, 27, 64, and 125. And 70 lies somewhere between 64 and 125. So we know that our answer is going to be a 4 with a decimal point. Now with the decimal, take a look. 70 is 6 away from 64 and 55 away from 125. So we will find this decimal point by taking the 6 and dividing it by the difference between 64 and 125, or 6 plus 55, which is 61. And we get an approximation of 0.1. And we'll write that 0.1 right there. And this is our approximation, or sorry, an estimate of cube root of 70. Now, what about cube root of 20. Let's write down all our cube roots. And the 20 lies somewhere between 8 and 27. It is 12 away from 8 and 7 away from 27. So our answer will be 2, because we're always choosing the lowest root, and it's going to have a decimal point. What's that decimal point? That decimal point will be decided by 12 and 12 plus 7, which is 19. So our answer turns out to be 2.6. The calculator actual answer is 2.7 and keeps going. And that's okay. This estimation procedure works on most cases, but it will be sometimes off. So even though it was off by a 0.1 of a decimal, or just the first decimal, it's a pretty good method to estimating cube roots and square roots.